Much, ma'am, for introducing me and giving me a chance to say a few words regarding the singular value decomposition and its application in front of you.
Yeah.
Basically, I'm working in approximation theory, and this approximation theory is applied to many of the branch of mathematics. When the students are in school level, they started using the approximation. For example, when they are in the 7 or 8 standard, they started using the value of pi by approximating 3.14. So this is the first step where the students have get touch with this approximation of a number, and when they grow up little more, then they have started maybe in 12th standard or 11th standard, they have approximating a function with the tangent at a point. For example, there is a function and a tangent is there. So at that point, this tangent is approximating this function. When you go away from that point, then the the error will be large. So in that sense, there is a in approximating a function for a point, the tangent is there. The third things that I want to emphasize, when they grow a little more and they go to the undergraduate levels, there they approximate a function with Taylor series. Now, when I'm saying function, it is not all functions. It has to be satisfy certain conditions. Okay, so basically, complex function can be approximated by the Taylor series. Then they go to the maybe furthermore, they also approximate this instead of Taylor series, they have approximate with the Fourier series. And when they go to the postgraduate level in functional analysis, if you have this set of U1, U2 up to so on, which is a orthogonal basis in a Hilbert space, then you have the any vector x in a Hilbert space can be expressed as summation of un x dot un as n tends to infinity. Now to approximate this, obviously we required certain finite quantity, and this component is the same. So we are approximating this any value of x with this finite number of terms. So this is when you go to the further level of your study in Hilbert space. Also, we are using this approximation things. Now here I'm talking about furthermore things is that is the sixth one that I want to say. It is a data uh, science or data analysis. So basically, what in data analysis, when we have a big data, there is a problem of reducing the data with the certain scenario. So this singular value decomposition, which I am going to talk today, is will be helpful to some of the handling some big amount of data you have. So it is a basically singular value decomposition will work with the reducing your data science, and the application of that one in the image processing with the fingerprints analysis. When we have a fingerprints is there, then we need to analyze the fingerprint, two fingerprints, then we need to match them. Then this data analysis tool or could be an approximation tool of that fingerprints what we have, it will be useful. And the This approximation theory is very big subject. So I'm talking here little bit of that one called singular value decomposition. In short, it is known as SVD, singular value decomposition. Now let me talk about that. Suppose you have given some vector, the vector x bar, if I can take as 1, 3, and if I apply some matrix, let me take this matrix as 2, 1, minus 1, 1. If I apply this matrix onto this vector, then what will happen? There is another new vector can be produced. So let me calculate that. So we can see that it is 2 plus 3, it is 5, and minus 1 plus 3, it is 2. So what this matrix does to this vector? Let us see by geometrically. So we have the x-axis and y-axis coordinate system we can have. We have, this is x-axis and this will be y-axis. On x-axis, these are the points. I'm just taking some coordinate system here. The point 1, 3, so it is 1 here and 3 here. So this point is, gives you this. This is the vector x bar. And this y bar, which we have produced by applying the matrix A to the x, it will have at 5, 2. So this is 5 and 2 here. So that vector will be here. Go ahead with the another color. So this is y bar. So what will happen to this vector x? Its two operation has been done here. The first one is the rotation, and then it stretch the vector. So when you have a matrix, when you apply to the any vector, it will basically two linear operation can be done. It will rotate the vector and stretch the vector. So that two operations can be done, can be happen when you apply any vector onto, means if you apply any matrix onto any vector x. So this type of operation will be there. So two operations, that means a stretching and the rotation. In matrix analysis, or I can say in linear algebra, probably those who have studied it, they have learned the matrix, this matrix, that is cos theta minus sin theta, sin theta minus cos theta. It gives you a rotation matrix amount. How much rotation is a theta rotation? When you, this is, if you are, this is B vector. If you apply this B vector to any, this B matrix to any vector, then what this matrix will do is just gives you a rotation from one vector to another vector. And if you want to see the stretching, then you can apply the C matrix, that is alpha 0, 0 alpha. So this is how much stretching is there. For example, if I apply this C matrix onto this 1, 3 vector, then you can see that the resultant is alpha 3 alpha. Suppose the value of alpha is 2, then that resultant vector will be 2, 6. So what is that does? It is just stretch the vector with 2, 6. So it is just stretching, no direction change or no rotation is there, only stretching is there. So this is this matrix which we have, it is a diagonal matrix which is gives you a stretching of any vector. And this matrix, any matrix A, not only of 2 by 2, but if you can go for the further dimension, any matrix will be a combination of the rotation matrix and the stretching matrix that we have. If the value of alpha is bigger than 1, then it is stretch the vector. If the value of alpha is smaller than 1, then it is compress the vector. So that is the things it will happen. So this is the basic idea regarding this matrix applied to a vector. Now with regards to that, in undergraduate levels, maybe students have learned regarding the decomposition of a symmetric matrix. There, the students have learned that if A is symmetric, then there exists invertible matrix. P such that A is equal to P D P inverse, where D is a diagonal matrix, P is can be calculated using the eigenvector of the matrix A. If A is symmetric, then you can have a decomposition of A where this P is actually an orthogonal matrix, and which will represent the rotation of the matrix. D is a diagonal matrix, so it will give you a stretching components. And again, there is a P inverse, which is also gives you a rotation. So it is actually what is happening, it is changing its basis from one basis to another basis, and basis also stretch the things and rotate the things for a symmetric matrix of order n by n. So it is a square matrix. If it is symmetric matrix, then there is a picture of this quantity, that means the stretching and all sort of things we have. So when how the symmetric matrix will behave, we have a picture. Now the question is, what will happen if A is not a square matrix, not a symmetric matrix, it is of order m by n. So if it is of this order, then what is the situation? How much rotation is there? How much stretching is there? That people want to understand. So for that, let us have some certain idea. Suppose I'm taking two orthogonal vectors, that is not orthogonal, but I'm taking orthonormal also. So I'm taking two orthonormal vector. Let me take is v1 bar and v2 bar. That means they are onto the one unit circle. So I'm taking a set of vectors on this unit circle, orthonormal. Okay. Now when you apply the matrix A onto this two orthonormal vector, that means it forms a basis of that dimension, because there is a two. So I'm taking in two-dimensional space. So I'm taking two orthonormal vectors. That means they forms a basis for that dimension, and that rotates, that transform to another space. So this vector which we have v1, what will happen to this v1? It will stretch and it will rotate. Okay, so let me take this v1 vector will be stretched like this. Let me take. So it will be stretched and it is rotated here. So this is the another vector which we have, which is the unit vector. So I have a unit vector here, which is u1 bar, and this vector v2 is transformed to another things that we have. It is this. Let's say this is transformed to v2 in this form, and this is the vector v2 bar. So this orthogonal system is transformed to this orthogonal system, and what will be this set of points which we have onto this circle, that here transform onto the in this manner. So what will be this representing? This will representing a sphere. Okay, sorry, this will representing an ellipse. So this is an ellipse. So the if you apply a matrix onto the set of points on the circle, it will transform to a points onto the ellipse. This is a 2 by 2 matrix. If it is applied onto the system, then this will happen. Now what is this? How much stretching is there? So what is this vector? Entire vector which we have here, it is sigma 1 u1, and this vector which we have, total vector, is sigma 2 u2 bar. What is this sigma 1 and sigma 2? It is that many stretching is there, and u1 gives you a direction. So you have a, this is the axis, and u1 and u2 are the principal axes of this system, and this sigma 1 and sigma 2 are the stretching. Now the same concept you can apply, you can thoughts for the higher dimensional space. That means if I have an n dimensional sphere, suppose in 3 dimension we have a sphere, okay, in 4 dimension it is known as hypersphere, and if you go for the further dimension and if you increase your n, then you have a hypersphere, and that hypersphere will be changed if you apply a onto this, will be changed to n dimensional hyperellipse. Okay, so it is n dimensional ellipse will be changed. So what we have into the n dimensional spheres, you have some vectors v1, v2, vn vectors, orthogonal vectors you have. That orthogonal vectors, by applying a onto it, will be changed to another orthogonal unit vectors, that is u1, u2 up to un. And in each direction, there will be a stretching of some quantity. So in each direction, amount of stretching is there of sigma 1, sigma 2 up to sigma n. And this is a stretching will be there. So what is happening is you have a matrix A which is applied on this V1. It will produce a new vector, that is sigma 1 U1 bar. And this will happen to each and every vector of V1, V2 up to Vn. So you have A of Vi bar is equal to sigma I Ui for every I running from 1 to up to n. So this is the situation is therefore uh, any matrix which is applied onto the this uh, set of vectors, orthogonal vectors. So what is, let me draw this is things into the picture manner. That means I have a matrix A, applying that matrix onto the V1, V2 up to Vn, and the resultant things which we have, it is this set of values that I can write down in u1 bar, u2 bar up to un bar, and here you have another matrix sigma 1, sigma 2 up to sigma n, and all rest of the values are 0. So it is a diagonal matrix you have. So when you apply this, a v1 will be gives you sigma 1 u1 and so on. So that the set of all these equations can be represented in this matrix form in this manner. So what we have, it is A V is equal to, this is U. This is notation for this matrix. It is, they have used sigma. So you have this equation AV is equal to U sigma. And since this U1, U2 up to Vn are orthonormal vectors, this is orthogonal matrix. What is orthogonal matrix? Is A transpose is orthogonal matrix is A into A transpose is equal to identity, which is A transpose into A. That means the inverse of the matrix A is transpose itself. This is the definition of orthogonal matrix we have. So this V and this U are orthogonal matrix. So if I apply this V onto that side, that means we have V into V transpose, A into V into V transpose will be U sigma V transpose, and V into V transpose will give you identity. So you have this matrix A can be converted into U sigma V transpose. So this is gives you a rotation. That means the orthogonal things. This is form of a stretching, and this is again a rotation. And this things is applied for any order matrix. That means any of order m by n matrix is there, and this is the decomposition of that matrix can be done in the first. When you have a vector, it will rotate the vector, then you apply sigma, it will stretch the vector, and then again you apply the u, it will back to the position of so it is actually basis is changing from one space to another space. Okay, so the basis is changing, and due to this basis change, there are lots of dimension reduction problem can be solved. Okay, so this is just a rough idea regarding what is the singular value decomposition is and how it is work. So this theorem which I have told you in vague manner is says like this, that every matrix A order m by n has a singular decomposition. So this theorem tells you that the singular value decomposition is applicable for matrix A, and why it is called the singular values, this sigma 1, sigma 2 up to sigma n, they are known as a singular value of a matrix A. Okay, so that is that singular value decomposition is, it says like you have a which is m by n matrix can be represented as A is equal to u sigma uh, u sigma v transpose, where u is m by m orthogonal matrix, v is n by n orthogonal matrix, and sigma is n diagonal matrix that we have considered. So any matrix A can be expressed in this form. Now, as I told you, this u sigma is the diagonal matrix. So you have certain values here. These are the zeros. Then this values sigma 1, sigma 2 up to sigma n, they are uniquely determined. And ui and vj, that means we have a vector which transform from one basis to another basis. It is also uniquely determined up to the complex sign. Okay, so that can be determined. And now we'll see the how this singular value decomposition can be computed. Okay, so what we have, it is we have a which is A is equal to u sigma v transpose. Then we can do this product of this two, that means A transpose A. We have A is this, So we substitute that value transpose, and we know that AB transpose will gives you B transpose A transpose. So as per this, we can say that this is V, and transpose of a transpose is A itself. So due to that, we can say that this is V sigma transpose U into U transpose by using the associative property. U transpose into U is identity because orthonormal vector, sorry, orthonormal matrix. And so you have this quantity. Then sigma transpose into sigma will gives you sigma square. And what is this? It is this is one matrix is equal to V sigma V transpose, and you can just remember means um, remember the things which I have told you, that if A is symmetric, then A can be represented as P D P inverse or P transpose, where P is orthogonal matrix. So here is the same situation we have. This is A transpose A. We have, which is a symmetric matrix. You can just check that this is nothing but the A transpose A. So this matrix A transpose A is a symmetric matrix. So, and that symmetric matrix have this decomposition. That means we have this. So that means V is nothing but the role of this P, and D is here sigma square. So the eigenvalues, so what is D is nothing but the diagonal of that one is the eigenvalue of it. So the sigma square matrix is there, they are the nothing but the eigenvalues of A transpose A. And V is nothing but the eigenvectors you can write down in the column manner of A transpose A. So to compute the singular values of this, you need to compute the sigma square, which is the eigenvalue of A transpose A. And to compute V, you have to compute the eigenvectors of A transpose A. So that means that the eigenvalues of A transpose A are the square of singular values, and the square root of that will gives me a singular values of the matrix A. So we have this relation. This lambda J is the eigen values for this A transpose A. Sigma square is the singular values, and V is the eigenvector of A transpose. In similar manner, we can compute U in the same manner as we have did in the previous things. Here we have A into A transpose we have did, and A into A transpose is also a symmetric matrix, and that's why it is have this decomposition. So here is also this sigma square is the eigenvalues of this, and it is the fact that A transpose into A and A transpose A, both of them have same eigenvalues, but the eigenvectors are different. So that's why it is U is the eigenvectors, means the columns of U are the eigenvectors of A into A transpose. So to compute the U, you have to compute the eigenvector of A into A transpose. To compute the V, you have to find out the eigenvectors of A transpose. And we have the things we have. For example, if I have this matrix A is 1, 2, 2, and we know that it has only one column, so the rank of this matrix will be 1. Okay, so it will have only one singular value, which is non-zero. All other values are 0 because its rank is 1. That is also one of the fact that I'm telling you. That means whatever the rank of the matrix you have, that many non-zero singular values will be there. And in that way, it is the linearly independent solutions you can get into the singular value decomposition. and it is very helpful. So we notice that this A transpose A is 1 by 1 matrix, and A into A transpose will be 3 by 3 matrix. This is 1 by 1 and 3 by 3 matrix you have. So both have the eigenvalues 9 and whose roots is 3, square root is 3. So the 3 is the singular value of this matrix. See, if you can just have dot product of this 1 minus 1 2 2 and minus 1 2 2. If you do the product of this, this is 1 2 3, 3 by 1 column. This is 1 by, sorry, this has 1 row, so 1 by 3. So the resultant matrix is 3 by 3, which is A into A transpose, and A transpose into A is, sorry, I might be making a mistake. Here it is, these two quantities are interchanged, should be there. So this column matrix here, this is minus 1 2 2 and minus 1 2 2 column and row matrix is there. So if we product them, what will happen? It is 1 minus 1 into 1 minus 1 will give you 1 plus 4 plus 4, so it is 9. So that 9 is the eigenvalue, because this matrix, sorry, not this one, A transpose into A is matrix 9, and that matrix 9 is 1 by 1 matrix, so the eigen value is 9, so that we have here, and the square root of that it is 3. Similar way you can calculate what is A into A transpose, which is 3 by 3 matrix. Okay, so I have already calculated what is U, what is V, and what is sigma. This is U, sigma, V transpose. Since it is a 1 by 1, it is same. So this is the singular value decomposition of this matrix A, where these columns are nothing but the eigen values A into A transpose, eigenvectors of A into A transpose, and so on. Now this is the that I have given you the idea regarding how to compute the singular value decomposition, and how to deal with um, the singular value if you have a problem is in front of you. But now I'm going to talk about the one of the application which I told you in the starting of the lecture, that is application in the data science, or I can say in image processing by fingerprints. So suppose we have a satellite which take the picture and want to send that picture to the earth, and the picture may contains 1000 cross 1000 pixels in millions of little squares, and each with the definite colors. So as you have, whenever you see the images, that images are actually a one of the matrix, and each quantity here, that means it's divided into some number of rows and column, and each of that quantity is gives you definite color, and that definite color have some value. So that picture a satellite want to send to the earth, having 1000 cross 1000 pixels in it. So this is one pixel, another pixel, and so on. So this picture satellites wanted to send to the earth. But we can code the color and send this many numbers, because this multiply by this will be this many numbers, and that many numbers need to transform through from satellite to earth, and it will take lots of time because satellite will take the pictures very frequently, and so it is a huge data will be there. Okay, so inside the information, it is better that we can send the essential information what this 1000 cross 1000 matrix contain, instead of sending this many numbers. So whatever the important essential information that image will have, that quantity we need to send to the author, not entire matrix. Okay, so that is the situation. So to do this, SVD will be helpful. Typically, the singular values are significant and other extremely small. So if we only keep only 20 singular values and throw away with the 980 singular values, only 20 columns of U and V we can send to the earth, and 20 singular values, that will work, that will reduce the image size, and more picture can be sent in limited time. So the other 980 columns are multiplied with this by small sigma that bring ignore. So what we can do is, with the help of matrix multiplication, column times row, that means this A is U1 sigma 1 V1 transpose. So this is the first column. So this is U1 U2 up to UN. You have a sigma here, and you have a V1 V2. So the first column is multiplied with the first value, and that is with the first column of V1. So that will gives me a first value. Second value, the second column of this will multiply the second singular value and the second column of this, and so on. So this, only this many items we need to send, not entire matrix A. So any matrix with R matrices with the of rank 1, only 20 terms to be kept, and we send only 20 times 2000 numbers instead of this much. Instead of this much, we only send 20 times 2000 numbers. So you can just see that how this 1000 cross 1000 number in comparison of 20 cross 2000 number. So it is actually, instead of 25 we are just sending 1. In of 25 numbers we are just only sending 1. So it is a very much dimension reduction problem is there. So it is actually we are sending the approximation to that image. So at first you see nothing, and suddenly you can recognize everything. Okay, in the when you apply a singular value decomposition. So the cost of computing SVD has become much more efficient but expensive for the big matrix. For example, here I have just gone through with the one example in R. So in R there is a library called PNG, and that library allow us to introduce any images, any PNG images into the R console. And this is a command for that, read PNG. This is a name of the image which I have taken, and I'm just storing that image into the variable X. So loading PNG file into the R, we have this command. I'm applying that. So this is the, we have a pencil, which is also inbuilt command in the R, which gives you this output. That means 600 cross 465 cross 4. Now this is number of rows and this is number of columns, and this 4 is a layer into that picture which we have. Generally the images are formed by red, yellow and blue color, RGB, red, green and blue. So here there are 4 layers in this picture. Now I'm taking only one layer of this picture. So for that, I'm applying only so for this X, which is we have a matrix. Now that image is not a image for R, it is a matrix for R. So that matrix have 600 rows, 465 columns, and four layers. Out of that, I'm taking all 600 columns, all 600 rows, and one layer, and store this new matrix into the X1. So this is the image of that X1. It's look like. So this is the X1 image is there. Now what I'm doing, there is inbuilt command in R is called SVD. So what is this SVD command will do? It will take the decomposition of that singular or decomposition of that matrix you have. So here just I'm storing this matrix as X red, and whatever the answer of this SVD become, we store into R dot SVD. Okay, now what we'll do is we just sending.
Prashant sir,
So we have A, which is U sigma. Yes.
sorry to interrupt you, sir. We have 10 minutes more to end this webinar.
Yeah, I will finish in 10 minutes. No problem.
Sure, sir. Thank you.
So we have this U sigma V transpose. So I'm taking just first column of this, one value from this, that is U1 is the first column of this U1, minus 1 and 1. So I'm just taking first column of that. First column of V, that is this as a matrix V minus 1, 1. So it is only one entry it will take, one column. And D, which is the singular value which we have a sigma, in that first value D1, 1, only one value. And I'm just making a multiplication of that too, that is U1 sigma 1 V1 transpose. That is U sigma 1 V1 transpose. This percentage, star percentage is the what we can say operator to multiply two matrices. And then whatever the resultant matrix we got, we have the image of that. That image is look like this. So this is the first approximation we can say. Next, I'm taking a 5 instead of 1. I'm taking a 5 columns of U, that is 1 to depth, that is 5 column. Then 5 singular values and 5 columns of U and V. So the 5 columns of U, 5 columns of V, and 5 singular values, and make the product of that and make the image of that. So this is the fifth approximation you have. Then I'm taking a 20th approximation. So 20 columns of U, 20 columns of V, 20 values, and that storing in the image, and that will be look like this. So you can just see that almost I can see that there is one flower is there, and there are some leaf. So information is retrieved only by sending, instead of 600 cross 465, instead of that only we are sending this much amount. And then to do the further approximation, I'm taking 40th. So 40 columns of U, 40 columns of V, and 40 singular values will make a product of that, and then we compress the image of that, and that will be look like. So this is the 40th approximation, and from this we can just see that almost all information can be retrieved from the previous things we have. So you can just compare the original figure which we have X1 which we have stored, and this is a 40th approximation, and you can just see that almost. And so this matrix is of order 100, sorry 6 400 something. What was I just 65 460 number of pixels, and this here we have already sent 40 singular values, 40 columns. That means 40 multiplied 600 and 40 columns of B. So 40 multiplied by 645. That many data we have only sent, and the information is derived from the original information that we have. So that's it for this lecture. This is my reference for from where I have prepared this lecture. There is very good book in the linear algebra and its application by Gilbert Stung. I have just prepared this lecture from that, mainly a theoretical part. And thank you very much for giving me a chance to deliver a talk.